Example 1. Solve each inequality, graph the solution if possible. So if we take a look at letter A, we have the absolute value of x is less than or equal to 3.5. So essentially what we're saying here is that we're saying the distance between x and 0 has to be less than or equal to 3.5. Well, before we actually go along with even solving that, let's think about that and think about what that would look like on a number line. So the distance between x and 0, and I know it's 0 because there's nothing in here with my x. So if I put 0 on a number line, I'm saying that the distance between any number and 0 has to be less than or equal to 3.5. So the distance could be 1, the distance could be 2, the distance between 0 and 3, but we couldn't quite go out to 4 because the distance away from 0 can only be up to 3.5. We could go the other direction, -1, -2, -3, -4, because distance is always a positive measure, so we could get out to -3.5 because when considering the distance, it's still a distance from 0 of 3.5. Now, it says that we can be equal to, so I'm going to put a closed dot, and I'm going to put a closed dot, and then from 0, my distance could go to positive 3.5, or my distance could go to negative 3.5, because again, distance is always a positive number. We can't have a negative distance. So if we're going to solve that algebraically, we're going to drop our absolute value bars, and we're going to have x is less than or equal to 3.5. Now, once again, we drop our absolute value bars, x, and we change our 3.5 to a -3.5. But when you do that with an inequality sign, essentially it's like multiplying or dividing by a negative number. So we also have to switch the inequality. Now, if I take a look at what we have graphically already, it says that our value, x, has to be less than or equal to 3.5. Okay, well, here's 3.5, and we went less than. It also says that x has to be greater than or equal to -3.5. So here's -3.5, and we're going greater than. If we take a look at what we have shaded, that is an intersection. So we're doing both. So algebraically, our answer could look like that. Another way of writing it, because it is an intersection, we can put our variable in the center. We could say our lower bound is -3.5, our upper bound is positive 3.5, and then x is either less than or equal to positive 3.5 or greater than or equal to -3.5. Letter B. The absolute value of k minus 3 is less than -1. So let's think about this. The distance between k and 3, some number in 3, has to be less than -1. Okay, so the distance between k and 3. So if I put 3 on a number line, I'm going to do the distance away from 3. Okay, how can your distance, how can an absolute value be less than a negative number? Think about that. If you take an absolute value of something, you have these absolute value bars. What do absolute value bars always do to something? Don't they make it positive because it's a distance, and a distance is always positive? So how are we ever going to do this and get a number smaller than a negative? So you'd have to get a -2 or a -3 or a -4. You can't. You can't take the absolute value of something and get a smaller less than -1. So guess what? This has no solution. So graphically, we wouldn't even graph it. It would just be a no solution. Letter C. The absolute value of n plus 2 minus 3 is greater than or equal to -6. So what I'm going to do first here is I'm going to try to isolate this absolute value, and I'm going to put my -3 to the other side. I'm going to add 3 to both sides of our inequality, and we're going to have the absolute value of n plus 2 is greater than or equal to -3. Now, This time, I once again see a negative over here. That kind of concerns me. And I'm saying, okay, the absolute value always has to be positive. Okay, so if I'm comparing absolute value to a negative number, that's kind of a concern. But this time it's saying, okay, the absolute value, the distance between some number and 2, has to be greater than or equal to -3. Well, if absolute value is always positive, okay, so this part is always, no matter what I substitute in there. I can pick any number I want and substitute it in there. I'm always, once I take the absolute value of it, going to get a positive number. Well, when is a positive number greater than or equal to a negative number? Well, that's all the time. So this time I'm comparing to a negative number, but I have to be bigger than the negative number. Well, that always happens. Versus if you remember our previous example, we were comparing to a negative number, but we had to be smaller. That never happens with absolute value. So this one is infinite solutions, which means graphically we can number our number line. I'm just going to put 0, 1, 2, 3, -1, -2, -3, and then graphically you would shade the entire number line. Letter D. 3 times the absolute value of D plus 1 minus 7 is greater than or equal to -1. So once again, before I take a look at this one, I'm first going to try, if I can, to isolate this absolute value. I'm going to start by adding 7. 3 times the absolute value of D plus 1 is greater than or equal to 6. I'm then going to divide by 3. The absolute value of D plus 1 is greater than or equal to 2. Now, this time I'm comparing to a positive number. That's a good thing because absolute value is a positive number. Now, when is the absolute value going to be greater than or equal to a positive number? Well, that's probably only going to happen at certain points because this absolute value could still probably be like 0 or 1 or something else, but I specifically want it to be greater than or equal to 2. So this one is not going to be a no solution or an infinite solution. It's going to have a very specific solution. In order to do that, we're going to drop our absolute value, and I'm going to say D plus 1 is greater than or equal to 2. So you kind of copy the problem. Then I'm going to drop my absolute value again, and I'm going to say D plus 1. And instead of 2, I am going to switch it to a -2. But again, when you switch the sign on the right-hand side, because it's an inequality, you also have to switch the inequality. Subtract 1, which is going to give me D is greater than or equal to 1. Subtract 1, D is less than or equal to -3. If we take a look at that graphically, I have a 1 and I have a -3. So I'm going to start, let's say, -4, -3, -2, -1, 0, 1, 2, 3. If I do D is greater than or equal to 1, I would put a closed dot at 1 and shade greater than. If I'm going to do D is less than or equal to -3, I'm going to put a closed dot at -3 and shade less than. And then if I take a look at my solution, this is not overlapping. This is a union, so I'm going to say or. And because it's an or, this is the way we would write it with two separate inequalities. We can't combine it like we can with the and.